So welcome back to the next session of the P block elements 2. In this content, we are going to look into the hydrochloric acid, its physical and chemical properties and the preparation, followed by its general trends in exhibiting its physical and chemical properties. Those are all the things which we are going to look into this content. See, the preparation of an hydrochloric acid includes the reaction between the sodium chloride and the sulfuric acid. The sodium chloride, when it reacts with the sulfuric acid, it forms sodium hydrogen sulfate, NaHSO4, then HCl. So one of the hydrogen will take up the chlorine and goes as HCl. And the reaction continues. The sodium hydrogen sulfate will further react with one more moles of an NaCl to form sodium sulfate, Na2SO4 plus HCl. So in this consecutive methods of preparation of the HCl, we are getting 2 moles of an HCl. If the HCl which we are getting is moist, we can pass through the sulfuric acid. Since concentrated sulfuric acid is an excellent dehydrating agent, it can remove the moisture from the HCl gas so that we will be getting a dry HCl so easily. So this is the one. Then its properties includes, it's a colorless pungent smelling gas, it's unpleasant smell. Then you can liquefy this HCl to a colorless liquid. The boiling point is 189 Kelvin. Then it can be frozen to the crystalline solid, white crystalline solid, which is colorless. Its melting point is 159 Kelvin, boiling point 189, melting point 159. This is more soluble in the water. That's why it forms an water molecule takes a hydrogen from this HCl. Thereby it forms H3O plus and Cl minus will goes out. We have seen this type of reaction in the unit 8 so much. Then its chemical properties. Chemical properties includes the reaction between the metal. We have seen these types of the reaction in class 11. Okay. Zinc reacts with an HCl to form zinc chloride by displacing the hydrogen in it. Then similarly any metals. Okay, any metals when it is reacts with an HCl or H2SO4, it displays hydrogen there. Similarly sodium carbonate. Sodium carbonate reacts with an HCl, so that sodium will take up the chlorine and goes as sodium chloride. Hydrogen will take up the oxygen and goes as water molecule. Carbon dioxide will take up the oxygen and goes carbon will take the oxygen and goes as carbon dioxide. Then the same thing happens for all. Okay, the product is NaCl, H2O and CO2 is common here. When it comes to the sulfide, the last one, sodium sulfide, here sodium will take up the chlorine and goes as sodium chloride, then H2O goes out, there CO2 goes out, here SO2 goes out. That's it. That's the only thing, nothing much more. So its properties includes colorless pungent smelling liquid, and it can be liquefied to the colorless liquid. The boiling point is 189 Kelvin, the melting point is 159 Kelvin. It has a great affinity to the water, which means it dissolves in the water to form H3O plus and Cl minus. The next one is chemical properties. Then after which, the very important chemical property is this one. The 3 parts of an HCl, 1 part of HNO3 is called as a royal water. We call it an aqua regia. This is widely used to dissolve the noble metals like platinum, gold, etc. The reaction is given. Stoichiometry, you have to keep it in mind. See, gold in the presence of an acid, nitric acid, in such a way you can take an HCl. Okay, the stoichiometry is 1414. Here, platinum reacts in the presence of an H plus, then NO3 ion from the nitric acid, Cl minus from the HCl acid. Stoichiometry is 316,418. Okay, in this way you have to remember the stoichiometry, only then you can do 1414, 316,418. Okay, so right side it is very easy. Nitric oxide goes out, water molecule goes out, followed by the formation of AuCl4 minus and PtCl6 minus, 2 minus. Okay, then use of an HCl. Use of an HCl includes, it is from the HCl we can able to displace the hydrogen from it, thereby chlorine gas can be produced. Then an HCl treated with ammonia, it forms ammonium chloride here. Then glucose can be prepared from the cornstarch, which means this HCl is used to hydrolyze the starch, so that we'll be getting the glucose. So that's the uses. Then it is widely used to extract the glue from the bone. Glue in the sense is the one which actually connects the patella and the bone. Okay, the purification of the bone black. There is a deposition of the charcoal, so you can able to remove it with the help of this hydrochloric acid. So this is what uses of this hydrochloric acid. Then trends. Trends includes hydrogen reacts with all halogens, no doubt in that, but the reaction happens at different temperature. Hydrogen reacts with the chlorine at the room temperature. Then hydrogen reacts with the fluorine with a violent reaction, which means large amount of heat energy will be released there. then the reaction between hydrogen, bromine, hydrogen and iodine is a reversible reaction and equilibrium is established between them. Okay. Then the displacement reaction. Any chlorides you can take or any sulfates you can take. If the chlorides have been taken on treatment with the sulfuric acid, this chloride will be taken up by the hydrogen and goes as hydrogen sulfate. Okay, thereby ionic sulfate. Say for example, if iron is taken, iron will goes as a ferric sulfate in such a way. Then hydrogen sulfate, which is hydrogen sulfate can be said as an H2SO4 or hydrogen sulfide, it is H2S, reacts with an ionic hydrides at the high temperature. Okay, so it can react with the ionic chlorides at higher temperature. So this is what. Then ionic fluorides can be converted into hydrogen fluorides with the help of this. Okay. So if fluorides are present, NaF can be converted into HF by treatment with an acid. Okay. Then HBr and HI is oxidized to H2SO4, oxidized by the H2SO4, so it cannot be prepared by this method. See, we can prepare rest of the things, but HBr and HI cannot be prepared because this sulfuric acid can oxidize the bromide to bromine, iodide to iodine. So Br minus 1 oxidation state goes to the 0. So that's the reason it cannot be done with this method. The next one is hydrolysis of phosphorus trihalide. When the phosphorus trihalide is hydrolyzed, we will be getting a phosphorus acid with the liberation of an HX. So we are preparing hydrogen halide in the whole content which we are saying it. See, except phosphorus trifluoride will not, phosphorus trifluoride alone will not react with the water molecule here. Okay. So assume that we are preparing HBr and HI. So we are taking PBr3 or PI3 as a paste. Okay. And to that bromine is added dropwise. Okay. Or iodine added dropwise. Otherwise, you can take you can make a paste of a red phosphorus. Okay. Then with the help of water, so that you can pass this bromine water dropwise, or you can pass the solid iodine, so that you will be getting hydrogen bromide, hydrogen iodine, just like that. Here assumes that since we are passing bromine and iodine, there are chances where it could escape in the form of a vapor. Those vapors are being collected through a column, where the column consists of a red phosphorus, moist red phosphorus. So moist red phosphorus will take that halogen, so that again it turns into phosphorus trihalide. Again the very first reaction takes place, the hydrolysis of a phosphorus trihalide, thereby hydrogen halide has been prepared. See, with the help of this, I can able to prepare hydrogen bromide and hydrogen iodide. I am coming again once more. See, the hydrogen halide, out of which it can be prepared by the phosphorus hydrolysis of a phosphorus trihalide. You will be getting phosphorus acid and hydrogen halide. In order to prepare that, you need to take the paste of a red phosphorus. To that, you need to pass the bromine liquid or the solid iodine, so that you will be able to prepare the hydrogen bromide and hydrogen iodide. Suppose if the halogens goes completely out as a gas, we have a column. Through the if you pass the gas through the column contains the moist red phosphorus. The phosphorus will again absorb that halogen, it turns into phosphorus trihalide. Again, hydrolysis reaction takes place for the formation of the phosphorus acid and hydrogen halide. That's the one. Next one, covalent hydrides. See, halogen reacts with an H2S to form hydrogen halide and sulfur. So halogen reacts with hydrogen sulfide to form hydrogen halide, HX, then sulfur. Okay. Then if you hydrocarbon, let me take benzene. If benzene, if halogen is treated, one of the hydrogen will take up the chlorine and comes as HCl. So your product is C6H5Cl. So this is, since we are preparing hydrogen halide, HCl is our main product here. Okay. Since the bond dissociation energy decreases down a group, the thermal stability also decreases down a group. So that's what, from fluorine to iodine. Okay. It is fluorine has a minimum bond dissociation energy, no doubt that. But again, if you move from, it is not a bond between F and F. Okay. Fluorine is the most strongest oxidizing agent because of the minimum bond dissociation energy between fluorine and the fluorine. Here, the bond dissociation energy, we are talking between hydrogen and the halogen. Between hydrogen and the halogen, the bond dissociation energy actually decreases from fluorine to iodine. Thereby, thermal stability also decreases from fluorine to iodine. That's the point. See, even at 400 degrees Celsius, HI decomposes, but HCF and HCl are quite stable at this temperature. This point actually clearly states, down a group, the bond dissociation energy between the hydrogen halide decreases. Next one. Next one talks about the percentage of an ionic character. Okay. If you look into the percentage of an ionic character here, percentage of an ionic character will obviously decreases from hydrogen fluoride to hydrogen iodide. Okay, as the size of the halogen increases, the percentage of an ionic character also decreases, because there are more, when the size of the halogen increases, there are more tendency for the cation to abstract an electron from the anion. Thereby, ionic character can be changed to a covalent character from the Fajan's rule, which we have discussed in the last year. Okay, then at the room temperature, hydrogen halide are gases, but HF can be liquefied because it has a tendency to form a hydrogen bonding. Okay, HF can be liquefied because it has a tendency to form an hydrogen bonding. See, hydrogen halide gases are colorless mostly. When the hydrogen halide gas is passed to the moist air, it forms a moist hydrochloric acid, hydrohalic acid with the white fumes, with the evolution of the white fumes. Okay, the melting point and the boiling point of this hydrogen fluoride is higher because of the formation of the strong hydrogen bond. This one we have seen already. I have said. Okay, because it has a tendency to form a strong hydrogen bonding, it shows high melting and boiling point. Similarly, this kind of an hydrogen bonding is not present in the other high hydrogen halides other than HF. Okay, the next one, acidic properties. This hydrogen halide is extremely soluble in water because it has a tendency to form an hydrogen bonding. Not only that, molecular association can happen with the hydrogen water molecule between the hydrogen halide and the water. Okay. All hydrogen halide except HF is a strong acid. HF is 100% a weak acid. Okay, no doubt in that. Because to illustrate that, 0.1 millimolar solution is only 10% ionized. But in 5 molar and 15 molar, HF can act as a stronger acid because of its equilibrium exhibition. See, 0.1 millimolar is a very less concentrated, but in that situation, in the same concentration, rest of the halide acids are quite strong. Okay, but here it is not so. Okay, this shows much strength only in the 5 molar and the 15 molar, between 5 to 15 molar. Okay, so that's why HF is a strong acid because of the fact that it attains an equilibrium. Okay, HF first reacts with the water molecule to form H3O plus by reducing F minus. Then this F minus can react with again one more HF to form HF2 minus. Okay, so equilibrium is established. Okay, at high concentration, the equilibrium involves the removal of the fluoride ion. When we are preparing this hydrogen fluoride at high concentration, we have to remove this fluoride ion that has been formed. Okay, because if actually we do not remove that, equilibrium attainability is disturbed. Okay, the dissociation will further suppress the common ion effect. Okay, that's the reason. The salt of the fluorine like sodium hydrogen fluoride and potassium hydrogen fluoride, ammonium hydrogen fluoride are stable because it forms these are all called as a dihalides. Okay, hydrogen dihalides because F2, right, HF2, HF2, HF2. So that's why it's an hydrogen dihalide. It's quite stable. These contents are completely informative. You have to study, that's all. Okay. The other hydrogen halides which we have seen, okay, other hydrogen dihalides also do not form hydrogen bonding here. Okay. Moist HF which is not dry rapidly reacts with the silica and the glass. Okay. HF has an ability to react with silica and the glass, thereby it forms silicon tetrafluoride and sodium tetrafluorosilicate. Sorry, hexafluorosilicate. Okay, so this is what Na2SiF6. Then oxidation reaction. Hi is used as an oxidizing agent, no doubt in that, because it oxidizes Hi to iodine. Hi will be iodine -1 is reduced to 2, oxidized to 0. So that's why it's as a reducing agent. Then acidic solution of the iodide is readily oxidized, which means iodide has readily oxidized because it acts as a reducing agent, which will oxidize itself by reducing the other substances. So it reduces starch. So this gives the color, pigmentation color as a blue color, blue-black color. And HBr is more difficult to oxidize than HI, because of decrease in the size of an halogen. Okay, HBr reduces slowly H2SO4 into SO2. Okay, but whereas HI will reduces quite fastly. Okay, that's the reaction. Then reaction is quite clear. Br -1 is oxidized to 0. Thereby it reduces +6 to +4 sulfur. The next one, HI and ionic iodides rapidly reduced by H2SO4 into H2S and not into SO2. See, hydrohalic acid here, HBr is oxidizing this, reducing the sulfur to SO2. But here, when HI is treated, HI reduces the sulfur with the +1 oxidations to -2, which means it oxidizes there. Okay, alcohol reacts with an HI to form an ethane. This one we have seen in the preparation of the glucose. When glucose is treated with HI and red phosphorus, we are getting NHN and iodihexane. So that's the what alkane you will be getting. Then when nitric acid reacts with the hydrofluoric acid, it will be getting a nitrous acid. Okay, by forming HOF. Then dinitrogen dioxide N2O2 reacts with HF to form ammonium NH4. Okay, these are all informative. Okay, then HCl is not affected by the H2SO4 but oxidized by MnO2, KMnO4 or KCl. HCl is not being affected by concentrated sulfuric acid, but the other compounds like manganese dioxide, potassium permanganate or KCl can oxidize that HCl. So that is regarding that. Next one, reactivity, the properties and its order. The very first one, reactivity of an hydrogen. Hydrogen reactivity actually decreases from fluorine to iodine. Okay, because HF, the percentage of an ionic and the covalent character changes from the HF to HI. Stability also decreases from HF to HI. Okay. Then volatility of the hydrides. Volatility is tendency to get into the gases. That increases from fluorine, iodine, bromine, chlorine. So this has a different fluorine, iodine, chlorine, bromine. Okay, have this order in your mind. Thermal stability. Thermal stability also the similar HF, HI, HBr, HCl, but the decreases. Then boiling point, chlorine, HCl will have show mole boiling point, then followed by HBr, then followed by HI, then followed by HF. Okay, acid strength increases from HF to HI. Yes, okay, because as the size of an halogen increases, there are more tendency for hydrogen goes as a H plus so easily. So that's the reason. Then oxides of an halogen, we have a table here. Okay, I will show that. See, fluorine will react with an oxygen readily to form oxygen, difluorine oxygen, in which the oxidation state of the fluorine is -1. Then next one is difluorine dioxide. The oxidation state is also -1 there, F2O2. Okay, except fluorine, all other halogen has a positive oxidation state. We'll see that. Except fluorine, then rest of the one will have a positive oxidation state there. Look at it. See, we have discussed this. Fluorine reacts with an oxygen to form a difluorine oxide, then difluorine dioxide. In both, the oxidation state of the fluorine is -1. Then other halogen actually do not react with the oxygen readily. Cannot react with the oxygen so readily. So, except fluorine, all other halogen have a positive oxidation state. So, fluorine alone has a negative oxidation state. Rest of the halogen have positive oxidation state. Look at here. See, the oxides formed by the chlorine, the oxidation state is +1. Here also it is +4, then +6, +7. Whereas if you look into the fluorine, fluorine alone gets the oxidation state of -1 here. So that's the reason. Okay, it has a minus oxidation state. So rest of the compounds exhibit the positive oxidation state, no doubt in that. Okay, the next one, oxoacids of an halogen. See, chlorine actually forms chlorous, hypochlorous acid. I would say there are 4 types of an acid: hypohalous, halous, halic, perhalic. So these are all the 4 categories: hypohalous, halous, halic, perhalic, in which the oxidation state of the halogen can be +1, +3, +5, +7. Fluorine forms just an hypohalous acid. Chlorine forms all the 4 types of an acid. Then bromine and iodine does not form halous acid, it forms rest of the acids. So this is the one we need to make. See, fluorine forms only hypohalous. Then chlorine forms all the 4 types of an hypohalous, halous, halic, perhalic. Then bromine and iodine do not form halous, but it forms hypohalous, halic, perhalic acid, in which the oxidation state increases from +1 to +7. So that's the one. Okay. So this is regarding the oxoacids of the halogen. See, in this content, what we have seen is the important aspect is to prepare the hydrochloric acid, the reactions involved in the hydrochloric acid, then followed by the general trends. General trends includes the informative content. You have to know what has been given and you have to put it in your mind. Probably it will be useful for 1 mark question. Then one question is asked frequently is, so why HF is a weak acid? Because 0.1 millimolar solution of an HF is weakly ionized. This HF is strongly ionized only at the 5 molar to 15 molar solution by forming HF and HF2. Okay, so HF2 minus. So that's the reason. That's the only important question that will be asked. From this 2 table, 1 mark can be expected. Okay, so that's it with this session. In the following session, we are going to look into the inert gases, then fast food. So with that, we are winding up with the. Thank you. See you all in the next session.